speaker this morning session is Professor Barbu from IASI, and he will speak about internal exact controllability and frequent stabilization of stochastic parabolic-like equations with multiplicative noise. Please welcome.
First of all, let me thank you for inviting me here. Well, the problem, in fact, I'm going to speak here, it is exact controllability about this stochastic semi-linear parabolic equation, in fact, and stabilization of this equation, and also its counterpart, Navier-Stokes equation. So, here, in fact, this equation is considered on a domain O, script O, and here O sub 0 is a subdomain of O. And what exactly means exact controllability? Exact controllability means, or consists, the problem of exact controllability consists to find a controller, adapted controller, such that this is the solution of this equation, which is all posed, of course, steer initial data x in 0 in a certain time, capital T. Stabilization means, of course, to find a feedback controller in this equation, such that feedback controller U in a feedback form, such as the corresponding closed loop system makes the system exponentially stable and probability. Well, in fact, okay, here WT, in fact, it is a Wiener process of this form. I'm not going to insist about this. And about, or condition about A, you are considering here as a deterministic, but you can consider as well the processes. A infinite, B is regular, F is Lipschitzian, F0 equals 0, of course. And as I said before, O sub 0 is an open subdomain of O with smooth boundary. Okay. So this means exactly what I said before, that stabilization means to find, in fact, to equal Fx, feedback control, which brings such that in probability asymptotic, the solution becomes asymptotically stable. And we are going to speak about this problem first, and also by its counterpart, which is Navier-Stokes equation, standard Navier-Stokes equation. Okay, the same thing about this one. We are considering here the Navier-Stokes equation, which in fact is Stokes operator perturbed by inertial term. So it's the same problem for Navier-Stokes equation. We're going to discuss this. Now let's come back to parabolic stochastic equation. Okay, I want to say that both problems I mentioned before, exact controllability and stabilization, are still open problems. Here I'm going to present only a partial result. But perhaps it's better to go to what happens in deterministic case. In deterministic case, so let's forget. In deterministic case, in fact, so let's forget this stochastic term. Here, we know that this equation is exactly controllable in any time. This is a result for heat equation established by Lebon and Robiano in 93. And after extending to this general situation here with A and B less regular by Fursikov and Emanuilov. I want to say that the exact controllability for deterministic equation is not a trivial result because it is equivalent with Karlman inequality for dual equation. And Karlman inequality, as everybody knows, is a very sophisticated, in fact, object. Now, but it was established, finally, Karlman inequality for the dual equation, in fact, deterministic one, as I say, in general form by Fursikov and Emanuilov. In fact, it was a consequence of Hermann and Karlman inequality established many years ago, but it should be put in a special term. So this problem was solved, but was solved very late, in fact, because this conjecture, the exact controllability of heat equation was conjecture, if I remember well, at the end of 60s, and was solved only 93 for heat equation, and then 97, 96, in fact, for this general equation. For Navier-Stokes, the situation is much more complicated. because it was conjectured the exact controllability for Navier-Stokes by Lyons in, yeah, it doesn't work. Yeah? Sorry. It's not open. Okay. So it was conjectured by Lyons at the end of 70s, if I remember well. It was solved only in 98 by Fursikov-Emanuilu. Before it was solved in 2-dimension, after in 3-dimension, okay, but finally it was solved in 98. But for corresponding stochastic equation, we don't know. We don't know if this equation is exactly controllable. We don't know if stochastic Navier-Stokes is exactly controllable in dimension 2, at least. No. Okay. Why? Why it is so difficult to establish exact controllability for this equation? Because exact controllability for this equation is equivalent with Karleman inequality for the dual stochastic equation. And dual stochastic equation, Karleman inequality, which is already very complicated for deterministic equation, is something, it is not known if this is a dual stochastic equation. In fact, Karleman inequality works or not. More precisely, it's not known if observability inequality for dual stochastic equation is true or not. So in absence of this tool, we cannot prove. Of course, some partial result, one partial result is a joint result with Rescano and Tessitor in 2022 published in AMO, where we proved, in fact, exact controllability, but not for all initial data. For initial data, a certain subset. In fact, we proved Karleman inequality for dual equation under certain conditions. But in general, this is not known. Of course, meantime, appeared a dozen of wrong results, okay, papers. But okay, this is we should excuse this because, in fact, it is a very complicated problem. Here, we'll see that you can say something about this in a very special case. In fact, we'll prove that we have an exact controllability. It's a competition. We have exact controllability in a special case here. Second problem is about stabilization. Also, in deterministic case, we know that this problem, which is called internal. Look here, in fact, why this problem is complicated? Because the controller is internal. It's with a support on a certain subset. It's not because if O0 coincides with the whole domain, it's no problem. So stabilization is the same thing. Stabilization for deterministic equation, also stochastic, and also this one is well known. In fact, for this equation was known, perhaps was Trigiani who established first the result. In fact, in 73, in for boundary control, but okay. And the final for Navier-Stokes is a joint paper with Trigiani in 2004. It proved, in fact, stabilization using feedback stabilization with finite dimensional controller U. Okay, so the problem this problem remains open here for this one and for Navier-Stokes. So we are going here to give first a stabilization result for this one, a stabilization result for Navier-Stokes, and finally to present or to see what we can say about exact controllability, which in fact it is. Okay, so let's go to stabilization theorem. Okay, I do not. Okay, so I consider you in a solution of this equation as a standard way, here, and let's design a stabilized feedback controller. We are considering, so remember in fact that O0, O sub 0 in fact, so this is our domain. This is our domain, and and this is a subdomain O0. We consider the domain Y sub 1, which is in fact given here, is this domain O sub 1, and consider the restriction of the operator A, that is of the Laplace operator on this domain, with Dirichlet boundary condition. Okay, this is defined, and consider the first eigenvalue of the operator A sub 1, considering this domain. Okay, so this one is defined as is well known, the first eigenvalue in this way. And finally, we are considering this feedback controller this feedback controller, in fact. And so the corresponding closed loop system with this feedback controller, if you put here, becomes this one. So this is a corresponding feedback controller with initial data and so on. And the main result is that if, okay, eta is, so the main result is if eta is sufficiently large, independent of x, of course, and if this condition is satisfied here, so the first eigenvalue for the Laplace operator corresponding to O1, in fact, this one here, minus this term here, which is function of the coefficient arise and of the noise, of course, is strictly positive. Then, for each x, in fact, the feedback controller exponentially stabilizes in probability equation 1. That is, happens what I have written here. So, here intervene, in fact, this term here is the first eigenvalue of Laplace operator under boundary condition on this domain O1. Okay, apparently, we'll give immediately sketch of proof. But let's discuss a little bit this condition, in fact. How can it make it more explicit? In fact, here, how to compute? We have a way, in fact, to compute this first eigenvalue for a subdomain. And the most famous, in fact, is, can say, classical Rayleigh was the first Faber-Cran parametric inequality in dimension. Here, okay, here is dimension 2, but works in dimension 1 as well, which is saying the following thing. This is the first eigenvalue of Laplace operator on a subdomain with Dirichlet condition here, satisfies this condition here, which is quite sharp, in fact, because it established, okay, it's not trivial, it's not immediate. So we have this classical is all from Rayleigh because it was after sharpened by Faber and Cran. Cran was in fact, who gave this formula. Where here it's omega d, of course, it is the volume of the unity ball. This GMN is the first positive zero of the Bessel function IM, and O1 is the volume. So this inequality, in fact, Rayleigh-Faber-Cran parametric inequality, allows us to give quite a good estimate for our stabilization, in fact, result. Because as a consequence, it follows this one, that if O1, this domain here, the volume, satisfies this inequality here, it involves only coefficient A, B, F, and so on, then the system or feedback controller for eta sufficiently large and positive is stabilizable, exponentially stabilizable. Now, so which is the conclusion? The conclusion is this: if this the volume is important, the volume of this of complementary domain. So we apply the control on O sub 0. This is support. If you apply our control here, then it is stabilizable for eta large if this volume, the volume of complementary domain, this crown, is sufficiently small. It's normal to be so. But what is interesting, in fact, it is not the shape which is important, but it's important the volume, in fact. Now, so it says that if this support, the support of our controller is sufficiently close, in fact, but everything depends on the coefficient, is sufficiently close of the final domain, then we have stabilization, in fact. Now, so it is an explicit result. So it is not definitive. It is not, does not answer to our problem because it is a conditional result, stabilization result. If you apply this proportional feedback controller on a domain which is, as is mentioned here, is complementary, sufficiently small, depends on the coefficient coming here, okay? 10, in this case, you have exact stability. I have here an example, in fact, to fix. The example is 1D because it's simpler to compute. But for instance, if you are considering this equation, stochastic equation, in fact, is one-dimensional, okay, sheet equation here. So if you are considering here, V here is a controller, and suppose that V, you are this controller, you are taking an interval a sub 1, a sub 2, so the controller is restricted, is a support in a certain interval, then it follows that this controller mentioned here, constructed here, for eta sufficiently large is stabilizable if this condition is satisfied, which is quite okay. This comes directly for the computation using the above formula. No, it is an elementary computation, but it's saying in fact what you could expect in general. So we can say how effective is our feedback controller. Now, it is effective if the volume is sufficiently small. Okay. This complementary. But what about the proof? In a few words, the proof starts with this inequality. This inequality, in fact, it is a consequence of Rayleigh's formula, in fact. That means if lambda 1, it is in general true. If lambda 1 star, in fact, the first eigenvalue operator of Laplace operator, then we have this inequality here. In fact, for for all y in H01 and eta sufficiently big. Okay, I do not insist about the proof because the proof it is use Rayleigh formula, in fact, mentioned here, and some okay analytic argument. So let's go on about this. Okay, so using this formula, because this is essential now, in order to prove that our system, closed loop system, that means the control system where we replace u by the feedback controller, then using Ito formula here, okay, standard Ito formula here, making some computation, we obtain this inequality here. So xt, k, I have denoted here by k this function, yeah. So we obtain this inequality, this equality here, kt is this guy here, okay, mt is a, okay, super martingale, it's obtained, xt, gamma. From here, under our condition follows it is k, it is positive, in fact. Yes, in fact, we have this inequality here by our condition here. So, mt is this martingale here, and so let's come back from this inequality, coming here, because coming to this equality here, because expectation of this is bounded, this is an increasing process, mt is semi-martingale, okay, this implies that there is a limit all this and this almost everywhere, okay, so it follows there is this limit, E gamma txt2, this is a norm in L2, and this implies, of course, stabilization. Now, it is in fact a variant of martingale convergence theorem, this one, no. So, this is, in few words, the proof. Of course, it is not essential that the function f as well as the coefficient might be processed in everything I said, because it's nothing special. Okay. Let's see what happens in Navier-Stokes. In the Navier-Stokes case, in fact, here is not exactly Navier-Stokes. It is Navier-Stokes perturbed by some terms. Of course, AT, where these terms come. For instance, if you subtract for Navier-Stokes equation a certain particular solution or a stationary solution, we obtain some linear terms. We obtain so-called Osen-Stokes equation, linear Osen-Stokes equation, a plus this inertial term will remain here. So I consider this Navier-Stokes equation. I mentioned before, in fact, we don't know if this equation is exactly controllable, as happens in the deterministic case. We don't know if it is stabilizable. That means find a controller ut in feedback form, which is with a support in a certain subdomain O sub 0, such as the solution is exponentially stable in probability. So here we apply, in fact, we have the same result. Let's, okay, is a usual condition about A and B, take free divergence field here, okay, introduce as happens on Navier-Stokes, it takes the space of free divergence vector H now. And okay, W is a Wiener process as in previous case. Introducing the operator we have here, okay, H and V. V is A is a Stokes operator, P is the Ray operator. You can write this equation, of course, as a differential equation, a nonlinear differential equation is a space H. But now let's consider as before, consider the operator A1, which is defined by O1, is on the same domain, O minus O0.
What's the noise in this case?
Excuse me?
What was the noise in this case?
It's a Wiener process. It's this one. It is. It's a Wiener process of the form of the same form, in fact. But A is this in this case is taken. In fact, it is EKC2 is an orthogonal basis in H and mu k in R.
So it's DWT. It's not X times DWT.
No, no.
Okay, so that's
Okay.
what the type
So, okay, so I introduce the same operator A sub 1. In fact, it is, yeah. So considering the same operator A sub 1, in fact, it's Stokes operator on this domain, O sub 1, O minus O sub 0, with usual condition. We denote this time the same, the first eigenvalue of the Stokes operator here, now, and it follows as before, as in previous lemma, that we have this dissipativity inequality here, and are considering this linear feedback controller. Well, if you consider, let's denote this gamma, in fact, the supremum for Beiji. Okay, this is something which arises from computation. It follows as a closed loop system with this feedback controller. In fact, is stable, asymptotically stable, if this condition is satisfied, in fact. So this means that the first eigenvalue, 001, of Stokes operator, classical Stokes operator on the domain O sub 1 is greater than this guy here, where this gamma star was defined before, and this comes exactly for the noise. Now, of course, for eta sufficiently large, so we have stabilization probability here is like here, and also an L2 stabilization in expectation. Okay, here we have this condition here, so the first line as the first eigenvalue. Unfortunately, I don't know if in literature there is an estimate for the first eigenvalue of Stokes operator. I don't know, maybe, but I didn't find. In fact, I didn't. I looked and. But perhaps in some situation can be computed, in fact, or estimated quite correctly, which is this lambda 1. And so we get an estimate about perhaps the volume. I presume that also in this case happened if this is a volume that of the complementary domain is sufficiently small. In fact, our control is feedback linear control is effective. Okay, so the proof is essentially, roughly speaking, the same. This time we use of the fact there's a nonlinear term which before fx had a Lipschitz contribution. This guy is 0 because we have bxx or bxxx equals 0, and we arrive to a similar, in fact, to a similar relationship here. So this is a semi-martingale, okay. Everything, this process is increasing, okay. This is bounded expectation, and comes that this have limit almost everywhere when t goes to infinity, and from here it follows stabilization. So the conclusion, in fact, that for both Navier-Stokes and for stochastic, so for semi-linear stochastic equation, now we have this proportional, automatician calls this proportional feedback controller, is effective, is stabilizable on this domain. Okay. From here, we'll go to discuss controllability. Controllability, exact controllability, or we'll go directly to, okay, so we'll go directly to discuss controllability, exact controllability, in fact, for Navier-Stokes equation. But a similar result we have for parabolic equation, but of course, Navier-Stokes equation is more interesting from many points of view. Okay, so we are considering here our equation, but consider this time that our controller is of this form. a spatial form, so it's not x dependent. Mu j are processes, beta j is usually Brownian motion. So I consider this very spatial case. And try to prove that in this case, not try, prove that in this case, our equation is exactly controllable. Now, of course, as I mentioned before, this is only a partial result because my conjecture is that, like in parabolic case, as for Navier-Stokes equation, both equations are exactly controllable in finite time, but we'll come back on this problem. Let's see how to solve. In fact, in this case, this problem has a very easy solution. Why insist about it? It's almost trivial, but why insist about this? Because, okay, quite recently I saw in a journal, a very famous journal, this result proved on 20 pages, okay, 20 pages. And according to me, it was not necessary. And let me explain why. Okay, because in fact, they tried to prove Kalman inequality for the corresponding dual equation, for Navier-Stokes equation. For Stokes equation, it is enough to prove, okay? Using the same machinery, complicated machinery, which works in deterministic case, which is not longer necessary. So what is exactly I'm trying to explain now? That at least in this case, and maybe in other cases as well, exact controllability of this equation as of parabolic stochastic equation follows by an easy rescaling argument. Let me explain. So let's consider this transformation. So is rescaling your standard rescaling equation. So take x under this form. If you perform this inequality, you get for y this deterministic random equation. It's exactly I wrote here. Of course, the coefficient arising here, at, bt, mu tilde t, by mu tilde t, and okay, it's just the processes, in fact, now the because intervene here, as you can say, affects the coefficient of good. Now, let's perform here. Let's go from this equation. This equation, we still transform this equation for 10 because it's we cannot apply as a deterministic result in this case, and explain why. So let's transform this equation by, so introduce this new variable, zeta t exponential, this guy here. If you introduce here, we get this deterministic equation with non-random coefficient. In fact, d zeta minus mu delta zeta, at this one bt, and this guy from the right hand side we denote it is vt, this guy here. Now, what we have here, in fact, I forgot to say they are considering the linear case in this case, because if you get a linear case controllability result, it follows a nonlinear case by fixed point arguments. So our equation, in fact, is Stokes equation. Now we're working on Stokes equation, linear Stokes equation, linearized equation. So we transform this equation in a linear Stokes equation of this form, with smooth or non-smooth coefficient at, bt. This is not important, but real coefficient, and not a random coefficient. And this is a controller V. But for this problem, we have already this very deep controllability result I mentioned before. That means Fursikov-Emanuilov, which is true, as I mentioned, in dimension 2 and 3, which is saying that this equation is exactly controllable in finite time on each interval. That means there is Vt, okay, which is deterministic, of course. It is now such that the corresponding solution zeta satisfies zeta t equals 0. Now we come back to our y and get that yt, it is 0 coming back. So coming back to x, we find that xt is 0 almost everywhere. But careful here that our controller u from here, this controller v or z before, is not more deterministic, is random, because we have this transformation here. No? So our real controller, in fact, it is over V multiplied by this one. So the conclusion is the following coming back. That the conclusion is the following. That, yeah. So our equation, Navier-Stokes equation, perhaps it's better to come back again to Stokes equation. Linear. Okay, so this equation here, let's forget this nonlinear term here, because for linear term is another discussion. So this equation here, where W is a Wiener process, but of the form mu k t beta k, is a final combination. I'm not sure that it's necessary to be, but okay, this is a different, perhaps it's necessary. Okay, so this is exactly controllable in finite time with an adapted controller U. An adapted controller U. Okay, if you want to go to nonlinear case, because in nonlinear case, also in deterministic case, the exact controllability is only local. That means you should start with the initial data in a neighborhood of a stationary solution or of zero and control it. So let's come, so the conclusion, as I mentioned, that in this case, we have an exact controllability result for this equation. Now, this is in fact is adapted controller. With this controller we get. So there is adapted controller, so there's a solution X to phi 1 satisfies this one. Now the problem, why does not work this argument for general noises? Well, we attempted to say that this might work. So let's go here to this comments. Okay, this is some, this remains true in therefore complete Navier. This means for nonlinear case. It is interesting. For nonlinear case, perhaps you should use some fixed point argument. But the main problem is if this theorem remains for general noise, Wiener processor. Let me comment a little bit this in this discussion here. In fact, for the previous result, we have used a rescaling argument. In fact, was inspired, in fact, from several works we have with Giuseppe and Michael in a different situation, not here, but okay, we realize, in fact, that the rescaling argument is a wonderful tool for treating stochastic equations multiplicative noise because it reduces to random deterministic. But unfortunately, sometimes it changes the nature of the problem, in fact, because by this rescaling, a parabolic equation is no longer parabolic, or for Navier-Stokes it is more complicated. Okay, so by rescaling argument, we can reduce our equation. We're discussing this for parabolic equation because the same argument presented before, or for parabolic equation. So it's simpler to discuss this. So for parabolic equation, we're using this rescaling argument, y u omega tx, we reduce this equation to this random equation, exactly to this random equation with random coefficient. Here random coefficients are is a function of even if at and bt initial in parabolic equation are real deterministic, they are not processes. In fact, this is a processes because intervene here, in fact, in computation beta j. So the random coefficients, adapted processes. Okay, but anyway, for each omega in probability set, capital omega, this equation is exactly controllable according to result I just mentioned. In fact, Manuilov-Fursikov or Lebov-Robier, Manuilov-Fursikov, because they gave, is exactly controllable. That means that for each capital T, in fact, okay, we have a solution, we have a controller U, which brings initial data into zero in this finite time. So, okay, we attempted to say, okay, we found a controller U, which solves the problem. But the main problem is the following. From the construction of this controller does not follow that this is adapted. So if this controller is not adapted U, that means controller found from deterministic theory, we cannot come back to our stochastic equation. We can say that only this scaling equation is exactly controllable for almost all omega. We cannot come back. The main problem is this controller is not controller, because U is not unique, which assure exact controllability of this equation. The main problem is you can't find a controller U which is adapted in order to come back, because the equivalence between this equation and the equation we start from is only in this framework. In fact. This, in fact, is a big problem, well, which perhaps will solve completely the exact controllability. If you can construct an adapted controller. Of course, everything should come from the construction of exact controllable for this controller in deterministic case. In deterministic case, this construction relies, in fact, on an optimal control problem. It's an optimal control problem of this type. And I want to mention. If you have such a system there, we consider this one, minimum integral 0t, this norm ut in the space L2 in this case, or in other space, plus 1 over epsilon x yt square 2. So I consider for each epsilon this approximating control problem, which has a unique solution, of course, A epsilon, Y epsilon. U epsilon t satisfying, of course, the equation plus minus delta Y epsilon, okay, equals 1, 0 U epsilon. It turns out that Y epsilon, the U epsilon, with sub epsilon goes to a controller which so it turns out that U epsilon is convergent strongly almost everywhere. U epsilon is convergent strongly star star where Y star t equals 0. But it is not clear, as I said, if this controller we get in this way is or how to proceed, how to replace this process to get an adapted controller U star. Because in general this is not adapted. It's not adapted because we should take here, okay, if you want we can replace this by take expectation. But it is taken, in fact, we should take on the set of all adapted processes. When we take on the set of all adapted processes, we cannot use, in fact, you are obliged to use, in fact, the dual stochastic equation as given by this. So this is the main problem here. If we succeed to prove that such controller U, which brings Y sub x into origin, is adapted, this will solve the problem. I want to say something more, in fact. Excuse me, yeah?
When you say adapted, do you mean adapted to the solution? Or to
I mean, no, to the filtration, in fact, to the filtration.
but not necessarily to this.
No, it is a progressively measurable and progressively measurable, in fact, in this sense. Yeah. Okay, so if you have this, if you succeed to prove directly in this way, for instance, exact controllability, this implies immediately by equivalence Karleman inequality for the dual equation. Now, so we have two ways, or we prove directly, in fact, exact controllability, and from here we deduce, in fact, Karleman inequality, or otherwise we succeed to prove Karleman inequality. Karleman inequality, as I said, is a very, very complicated object for Navier-Stokes deterministic and for stochastic, even for linear parabolic equations. So there's something else. If you have an exact controllability result of this type, this implies by a certain argument also an exact controllability result, boundary exact controllability results. That means it is some trick which permits to deduce from exact controllability, internal exact controllability, boundary controllability of the problem, in fact. So, but still I'm speaking here about conjecturing hypothesis, because so far what we know, coming back to, in fact, to our equation, in fact, and coming back to our equation. So for this one, as far as regards exact controllability, so far we have exact controllability. This is the first paper I mentioned with Tessitori and Reshtan. For initial data in a certain subset, or in this case, okay, it's no conclusion, it's no condition of this, but we take a very spatial noise. The same thing for Navier-Stokes. And well, one might expect to, however, perhaps this will be solved sometimes in the future. Let me give now some of your references, perhaps about this. Is about, okay, about okay, about the effect this controller, feedback controller, I mentioned that, okay, it was already used in some paper before. This is a paper with Tessitori and Karl and Reshkan about Kalman estimate and controllability of linear stochastic heat equation in 2003, but as I said, does not solve completely problem, it's only conjecture. And for other results, perhaps you should mention also this paper by Tang and Chang, entitled 2099, which is also a partial result. It's not a complete result about controllability, yes. But of course, myself, I received meantime many papers for reviews. In fact, were now being, well, at certain point, because everybody tried to prove, in fact, Kalman inequality for stochastic, non-stochastic equation, which of course is very complicated, but at a certain point it was a gap. Okay, perhaps I should find here. Thank you.
Thank you very much. So we have time to discussion. There's plenty of.
Yeah.
Maybe I missed, but could you state a simple form of Karlemann's inequality? Because I don't know what it is.
Okay. Let me, a simple form of Kalman inequality for parabolic equations, the following. I write for parabolic, linear parabolic equation, and perhaps heat equation because it's the same. If you have, for instance, this equation, it is y equals 0. Let's take the dual equation, backward equation, delta p. Of course, the same thing happens if you have a linear term. Kalman inequality, or a simple form of so-called observability inequality, which is almost equivalent with Kalman inequality, is saying the following thing, that P0 is a log L2 is less than C, integral from 0 t, okay, put here our domain U, t squared, if psi dt. What this means exactly, if you have a subdomain O sub 0, okay, we can control. This problem is backward. We can control the value of P in origin by knowing the value of P on subdomain O0. From P, in particular, it follows this PT for each domain, for each time is this one. In particular, this implies unique continuation. That means if P is 0 on a subdomain, it is 0 everywhere. This is observability inequality. It's a weaker form of Kalman inequality, but it is enough to prove controllability. This is famous observability. It's hard to establish. Okay, so first proof of this was given by Robiano and Lebeau in 1993. Robiano and Lebeau, exactly for heat equation, for this one. And after extended for general parabolic equation with non-smooth coefficient of the type represented by Fursikov and Emanuello. Now, this is Kalman inequality. For stochastic equation, of course, you can take in, if you have the same equation, you have dx minus delta x dt equal xw. So we have the stochastic equation has this form t plus p plus p. Okay, is kw. So we have the stochastic dual equation. So it should establish the same type of result for stochastic dual equation.
Well, there is something wrong, right? I mean,
yes, it is some. It is one more.
I mean, in the statement, shouldn't there be
What?
Something as dividing by t minus t or something like that?
No, it is okay. It follows this. It is okay. It is a coefficient which depends of t. Depends of t. No, I fixed t. Yes, sure. For stochastic equation, it's much more complicated because there are one more variables. These k variables, and B smooth and so. So it is already this inequality is very hard to prove. It's not trivial. Okay, it requires 4 hours, in fact, proof. It is quite difficult to do for a graduate course in 4 hours. And for Navier-Stokes, it is terrible. The 30-page proof. It's very, very complicated. And stochastic, one expects to give in stochastic case. In fact, uses the same technology, but perhaps it's necessary a very sharp technology in stochastic case for parabolic equations.
Yeah, more questions, please?
Yeah, I was still a little bit puzzled about the type of the noise in the Stokes operator, right? The type of the noise, shouldn't it be, instead of writing down, I mean, this product, I think you cannot write down this product x of t times dwt. You have to put in the coefficients beta of your expansion. You have
You mean
you have to put it in your form, right? B of x. But I don't see that you can make the noise, I mean, divergence free and local. Multiplicative, local, and
You mean
divergence
here?
free.
this is a noise?
No, I mean, you wrote x times dw.
Yes, correctly. Yes,
But that's
it
not
is here. It
divergence
is
free,
x,
right?
in fact. Yeah.
AEK is divergence free, but I mean, not x not divergence free.
Yes, it is correct, but in general, when you take, when you take, in fact, in the spatial Navier-Stokes equation, we take already a spatial basis, in fact. Yeah, it's correct.
Yeah. So
It is correct.
It should be
Yeah.
that the
It's correct. And in the case you are considering EK, in the case you are considering K independent of psi, independent.
Yeah.
In the last,
Should be written differently.
this is only principle, because here what we are taking, in fact, it is a case, okay, in this case here, in this case here, okay, they are independent, in fact. It's independent of, here, for instance, it is independent of x, sure. Yeah. In fact, in Navier-Stokes, you should be very careful also with the transformation, because immediately we start from free divergence vector free and do not go in the same. It's correct. Yes, sure.
Are there more questions or comments? I think no. Thank you very much.